Hi, welcome to graphing sine and cosine. This is the second part of graphing sine and cosine, and it's going to cover horizontal transformations. The idea with this page is to talk about those horizontal components that we didn't get to last time with Miss White's video. So if you need to put a little reminder to yourself, maybe below the title there, these do look similar. That's because I wanted to remind us all of what parent sine and parent cosine look like, and so you have those up there as well. Last time Ms. White talked about D and A representing the components of sine or cosine that shift or stretch those functions vertically. So A is going to stretch the amplitude of sine or cosine. D is going to shift cosine or sine up and down. And the first bit of terminology that we're going to use for our first set of horizontal transformations is the phase shift. So a phase exactly is what refers to the x value where a wave is in its period. So the period, like Miss White described, it takes sine or cosine 2 pi units or 360 degrees to complete a full period. So this is also known as their cycle, right? It's just the it's just describing the revolution, how long it takes to complete a full revolution around a circle, which you all know now from the unit circle that it takes 2 pi units to get back to 0. So since the first period is the first positive cycle, that first period exists between 0 and 2 pi. So if we go and look at these cycles, our first cycle of sine, it's just a different way to say period. Our first cycle of sine starts at 0, and it's got to go to its maximum, then to a minimum, then to a 0, then to another minimum, the first minimum, and it ends at 2 pi, and then it repeats the cycle over and over again. So likewise with cosine, the first cycle happens between 0 and 2 pi. So that's the first cycle or first period because it's the first positive one. And we normally like to deal with positive graphs when we're talking about different types of functions. So we can shift that first period by modifying what's inside the sine or cosine transformation like this. So we have a new inside function to the sine or cosine function with a bx minus c in either. So the thing we're going to focus on, and I'll show you actually with this memory bank, is what are each of these transformations doing. What does B do? What does C do? So I'm going to have a little bit of an exploration here. I'm going to put this up on screen. So this is something on Desmos that I've made to kind of help illustrate this. The red function, that's our sine function. The blue function, that's cosine. And I just plotted them side by side. Our first periods are going to be shown here on this graph. And we're going to kind of track to see what they do as we adjust these numbers. So obviously D is going to move these things up and down. We'll leave them centered though at 0. And A is going to stretch them out. If we put that A between 0 and 1, then they're going to be super thin. And let me actually zoom. Well, no, I'm going to zoom it out maybe a little bit. Sure. So our A value stretches it. We'll leave that at 1 just so we can keep that constant. But our b value, so that b value, you can see it's right here. It's next to x. That is going to horizontally shrink if we have a lot of them, and it will stretch if we have a fraction of those b values in our trig function. You can see that whole function, that whole first period stretches out to be 5 pi. So it takes 5 pi units to complete a first period. You can kind of zoom out to see that in its entirety. So that's what B will do. B will stretch it horizontally, and C is going to shift things left and right, shift all the values. So it shifts the entire first period. And so normally, like if I were to modify these functions and not indicate the first period specifically, then it would kind of look a little mesmerizing if I changed if I had the entire function listed out here. It'd be pretty woozy to stare at this, but it's really important that we can modify the first period of these graphs, because we want to maybe shift it only a certain distance. It would kind of be irrelevant to shift this function too far to the left and right, because then we start having then we start repeating ourselves. Like we only need to shift it within the first period. So we only deal within the first period. So after looking at that, let me give us some horizontal transformation memory bank items. So the number of periods actually within 2 pi, if I can reverse this a little bit, oops. Number of periods within 2 pi, if I can put this back, so we can see. That's going to be B. So B is what we're going to write in our little box here. So I'm sorry if there's a bunch of windows on the screen. I'm going to leave that up so you can see. So B is what shifts our number of periods in 2 pi. So if I leave this if I make B 4, that means we have 4 periods in 2 pi. The period's length after being transformed by B is 2 pi divided by B. So this is really important for us to understand. So if I have 2 pi divided by 4, then that's pi over 2, which I hope you all can see. My new transformed period is pi over 2 long, because my B is 4. So the next thing that we're looking at is what happens, let me reset this a little bit. What happens when we manipulate C, right? Well, C shifts things, so C is going to influence how our period is shifted left and right by using C divided by B. Because B represents the length of the period, C directly relates to it. So we need to use B as well in this little, I guess, indicator for where the first period starts. So we use C divided by B. And if we want to know where the x value where the first period ends, then we'll take C and divide it by B. We'll take that where we start, right? Where we start plus P. So plus our period length. And then we can see where the first period ends. So it's really important to notice where certain things finish their cycles, where certain revolutions begin and end. So conceptually, the B value horizontally what does it do? Stretches or shrinks? I'll just say stretches are our functions. While c divided by b horizontally shifts. It's kind of redundant, but I'm going to say it. Horizontally shifts left and right. Right, so now we need to kind of practice recognizing that. You've noticed that this should look pretty similar to how you've worked with quadratics in the past. So hopefully that becomes a little bit familiar. I'm going to remove this window real quick so we have a little bit of less chaos. All right, so if we zoom in just a little bit, we're going to practice with just some equations, and then we'll work our way down to graphing some of these things. The first thing that I wanted you all to do is find the amplitude and the vertical shift for 1 and 2. You should, I'm going to leave this up to you because it should be fairly easy if you remember. And you can kind of denote these things with different letters. So you can try that out. Not too difficult to notice there. And I'm going to put up my answers for this at the end, by the way. Find the period in radians. So this is new. We're finding the period of 5 sine 4 theta minus 3 pi over 2. So we want to check. Okay, so 4 is my b, and you don't really need to write that down if you recognize that already. 4 is my b. The negative doesn't count. The negative, consider like everything in these functions looking like this. If like 3 pi over 2 is sitting on its own away from the negative. So 3 pi over 2 is equal to c. So if I need to find my period, I really only need b. So my period, if we go back to this, my period is 2 pi divided by b. So 2 pi divided by 4. And this is where fractions are definitely needed, and understanding what your greatest common factor is between the numerator and the denominator to help you simplify these things. So this is going to be pi over 2. Not a difficult fraction to simplify, but it will get you will get a lot of practice with these fractions. I guarantee that. So that's number 3. So just using 2 pi over b to discover that. So if you'd like to try number 4, try finding the period with 2 pi over b, and I'll show you the answers at the end. For the phase shift in radians, that's where we're using c divided by b, because we want to know where does this new first period begin. So the phase shift of number 5 is going to use c divided by b. So I noticed that my c is negative pi divided by 4 divided by my b value, which is 6. So dividing by 6 is the same as multiplying by 1/6. So my phase shift is going to be negative pi divided by 24. So in other words, this has been shifted left, and we're going to say that to indicate our phase shift, because just saying like equals negative 24 doesn't really say much. So we're going to say shift left pi over 24. If you want to say maybe PS is equal to negative pi divided by 24, that would work as well. You can probably think about what this would look like on a multiple choice test. If you were asked for the phase shift, we'd be more likely to ask, state the answer like this. Shift left pi over 24. So if you get a negative number for this phase shift, that means you're moving everything left into the negatives from where it started at 0. So number 6, try that out. I can already see that that's going to be a phase shift right, so that might help you out with that one. For number 7, we are looking at a cosine function, and we want to state the x interval of the transformed first period. So this is a weird, and you'll have to pardon my language on that one, like the language of the problem. I want to know between what x values does the first period, the transformed first period, exist. So we want to represent that with interval notation. That's why I say x interval. So we need to use everything here. So we need to use whatever our b is. So our phase shift is going to be c divided by b, which is 2 pi divided by 3 divided by 1/2. I'm going to zoom this in a little bit. Sorry if you're having to squint too much here. And I can see that's going to be 2 pi over 3 times 2, so 4 pi over 3. And that's 4 pi over 3 right, because it's a positive 4 pi over 3. So that covers my phase shift, and now we need to know how long is the period. So the period is 2 pi divided by my b value, which is 1/2, and that equals 2 times 2 over 1, which is 4 pi. So now I can figure out my start. My start is going to be, and I should use brackets because this is where my first period exists. So it exists from 4 pi over 3 to wherever it ends. So it would exist from 4 pi over 3 plus 4 pi. This would be the end. This would be where our function ends, which you can see that's this equation right here is what I'm doing to get that. So 4 pi over 3 plus 4 pi, that's not too great because 4 pi doesn't have the same denominator as my 4 pi over 3, so I'm going to change that. And this is the critical part. 4 pi is the same as 12 pi divided by 3. Just remembering how you add fractions, right? If you put this in a calculator, it could get really messy because you have a pi in there. It might be easier for you to leave the pi out and then add those fractions together and just put the pi back in at the end if you struggle with fractions. So this ends up as 16 pi divided by 3. So that means my full coordinate point is 4 pi over 3, 16 pi over 3 with brackets. Okay, so there is a bit of adding fractions there. All right, so I'm almost at 20 minutes. I'm going to ask you to graph these functions. And I've changed number 11 to a cosine function because they're all sine otherwise. So make number 11 a cosine function. And I'm actually going to give the answers to your teachers and let them kind of talk to you all about this with the practice as well. Or they'll just straight up share out the answers to you so you can see them. So thanks for watching, and I'll see you later. Bye.